Hello scholars, welcome. Mr. Hinkle here. In this lecture, let's figure out, why are there seasons? I think that you and I observe, we know, in one part of the year it gets cold. We got to put on all of our extra layers and clothing, our jackets, put the winter blanket on the bed. And then in another time of year, it's hot and we're wearing less clothing, maybe sleeping just underneath of the sheets and trying to get out of town for a little while. Well, seasons happen for very specific reasons that we're going to explain here today. So our objective is to describe the mechanisms or the mechanics rather of Earth's seasons and how they work, and then look at seasonal variability through both time and space. All right, seasons are a natural phenomenon. We have spring, summer, fall, winter. Most regions, not all, because various places on Earth have different climates, but most regions experience seasonal variations in temperature, in weather, and in the amount of daylight hours. And spoiler alert, seasons happen because Earth is tilted on an axis and Earth orbits around the sun, holding that axis fixed towards the North Star, or a single direction. But less arm waving, more actually explaining. Let's get into it. Our Earth is a sphere, and the Earth every day receives light from the sun. And that light is approaching Earth essentially from the same direction everywhere, because the sun is so big. Now, when the sun's light shines down on the equator, the angle is directly overhead, and that angle changes because of the curvature of the Earth the higher in latitude that you go. And in order to describe this, I have a light, and we're going to look at the distribution of light energy. So this light is putting out a constant power source. The amount of light is not changing. Now, when I angle this light really close, directly 90 degrees, the light makes up a very small portion of, it takes a smaller space than when I angle it 45 degrees. Now this light is taking up a greater amount of space. I'll go next to it. When I angle it near 90 degrees, it's taking up a greater amount of space. So directly overhead, 45, 90. Do you see that? Same amount of light, but the different angle between the light and the board disperses the light over a greater amount of area, which means that the light over the smaller area is more intense. Take this to our Earth at the equator, where the light is directly overhead. The same amount of solar energy is dispersed over a smaller area, meaning more heat. The higher up you go, the more it's dispersed over a great amount of area, meaning not as hot. Once you get up to the poles, it's over a great amount of area, meaning the poles are very cold. So what we have here is an unequal heating of Earth's surface due to the nature of Earth being a sphere. So this is a very important component. Intuitively, we know it's hot at the equator and it's cold at the poles. But why is it hot at the equator and cold at the poles? Because of the Earth-Sun angle, and energy from the sun is more intense at the equator, creating more heat than it is at the poles, where there is less heat, leading to a heat budget system where there's a surplus at the equator, a deficit at the poles, and Earth's oceans are responsible for transporting heat, helping Earth to maintain stability in climate. Okay, cool. So now that we've got this key finding, uneven distribution of heat because of Earth-Sun angle, we can start to get into exactly what's happening for seasons. So Earth is tilted on an axis at about 23.5 degrees. Let's just put the Earth here. And this is wildly important for creating seasons. Not only is Earth on an axis, but that axial tilt is constant as it orbits around the sun, which means that you may have heard of the North Star. Doesn't matter what season it is, if you're in the northern hemisphere that is, doesn't matter what season it is, the North Star is always the North Star because, I don't know if you can see the ceiling, but imagine a point way up there out in space. Doesn't matter where, it's so far away that no matter where Earth is, it's pointing to that star because the axial tilt does not move. So one reason for the seasons is the axial tilt that is fixed. It doesn't move. It actually does move. But for our lifetimes, it doesn't move. Milankovitch cycles, we'll get to that, natural climate variability. But right now, the reason that this year you and I are experiencing seasons is because Earth is tilted on an axis that is fixed towards a point. Not only does Earth rotate on a fixed axis, but Earth also, I'm going to embellish this axis to more than 23.5, something like this. I'm just drawing pictures so we can do what we want, right? But Earth also orbits around the sun once every single year. So Earth has an annual orbit, which gives us 4 seasons every single year. And it's like this. Let's say, oh, I'm going to put the equator on here too. There's the equator, there's the equator, there's the equator, there's the equator. So what I would like you to note, let's go to where I live, Fresno, California. And it's up here in a mid-latitude region. And up here in a mid-latitude region. So notice, the sun, because of the tilt of the axis, where I'm at is further away, which creates a greater area for heat to be distributed. And then when Earth is pointing towards the sun, it's a smaller area. So when Earth's axis is pointing towards the sun, it would make sense that we are experiencing summer or winter. Less area, more intense. It's summer. You got it. And then 6 months later, that same amount of solar energy is distributed over a greater amount of area, which means that the intensity decreases, thus giving us winter. So we move from the shortest day of the year, because also this changes the amount of daylight, where it's the coolest, or relatively, through an even 12 hours to the longest day, and through another even day back to the shortest day. So axial tilt being fixed, annual orbit, gives us seasonal variability. Pretty cool, right? Well, what we see here then is this is actually flipped backwards, so the axis is tilted towards the Earth. In the northern hemisphere, we have the summer solstice, the longest day of the year, that moves through the autumn equinox, an equal length of day, to the winter solstice, the shortest day of the year, to another equinox, equal day. And it has to do with the Earth's axis tilting towards the sun or away from the sun. I think I just described this one again. I did both of them, so I'm going to move on. So let's talk about the variability through time and space. Well, at the tropics, the regions near the equator, this is relatively consistent sunlight all year long. There's less dramatic seasonal changes because the equator has the less fluctuation in the uneven distribution of Earth's light. The Earth-Sun angle is relatively unchanged. Mid-latitudes have 4 very distinct seasons: fall, summer, winter, spring, receiving varying amounts of daylight. This is kind of our example here. The Earth-Sun angle changes tremendously. And then polar regions have extreme seasonal contrast. The summer has a 24-hour daylight called the midnight sun, which we can see here. The sun goes down close, but it doesn't go all the way down, and then comes back up. And then 24-hour darkness in the winter for the polar night. Now, there's some misconceptions that the distance from the sun is going to change. Actually, the distance has little effect on the seasons. Earth does orbit the sun on an ellipse, and that ellipse changes. But from year to year, that impact is not as great as the tilt of the Earth and the changing Earth-Sun angle. This is where all the money is. It's the Earth-Sun angle changing the intensity of the sunlight that's coming down to a certain region on our planet. And then also, the equator does experience seasons. It's not a dramatic temperature swing, but what we usually see are wet and dry seasons, sometimes called monsoon seasons, that can lead to seasonal flooding. So while it might not be a 4-season kind of thing that's occurring like in mid-latitudes, there are definitely seasons in the equator. Now, this is a bigger conversation on Milankovitch cycles. Please see my video on this. But there are long-term changes in seasonal variability that have to do with the orbit of Earth changing its patterns, the eccentricity, the tilt changing its directions between 22.5 and 24.5, and then also the precession. So the North Star isn't always the North Star. Sometimes the Earth wobbles like a top, changing Earth-Sun angles yet again. So these are the drivers of natural climate variability that are identified as Milankovitch cycles. Now, in conclusion, seasons occur because Earth has a fixed axis tilted towards the North Star, and Earth orbits the sun every single year, which ends up affecting the Earth-Sun angle. Thank you so much, and I'll see you again.